Now that we have gained the background in Newton method of solving for the roots of a single nonlinear algebraic equation or a system of nonlinear algebraic equations, let's turn to a few examples. This particular example that you see here is taken from a previous tutorial problem where the flash process is described in detail, the mass balance equations are provided, the thermodynamic equilibrium relationships have been explained there. To just elaborate a little bit, so you have a feed stream with flowing with a flow rate of F and which has got composition of Zi. I goes from 1 to n, where capital N is the number of species that is part of that stream. So you have a feed stream with a certain composition, and that stream is flashed in this vessel, which is called a flash vessel. And what happens is you get a liquid stream with flow rate L and a vapor stream with a flow rate of V coming out of it. The exiting liquid and vapor streams are in thermodynamic equilibrium, and that is what, in a very simple form, it is modeled as yi is equal to ki times xi, because the k value for different species can be different depending on their volatilities. And in general, this ki will depend on temperature and pressure, but here we are going to assume that ki's are constant and the values are given. So the yi's are the compositions of the species in the vapor stream, and the xi's are the compositions of the species in the liquid stream. And because they exit that vessel, we assume that they are in thermodynamic equilibrium. So the composition of a particular species I in the vapor stream is related to the composition of the same species in the liquid stream by this kind of a simple relationship, right? So this is a linear thermodynamic relationship that we have. So what you can do is you can write the overall mass balance, you can write the mass balance for the individual species, and then you can link the liquid and vapor phase compositions through the thermodynamic relationship that we have listed here. So you get a system of equations actually, right? So for example, the independent number of mass balances will be n of them. So you can take the overall mass balance and the species balance for n minus 1 species, or you can take the species balance for all the n species, right? So you'll have n mass balance equations, and then you have n thermodynamic relationships, all right, between the liquid and the vapor phase compositions. So you will get a system of equations actually, and you have to solve for the unknowns. The unknowns are V and L, the flow rates of the product streams, the compositions of the liquid and vapor streams. So you have, just listing here, we have 2n plus 2 unknowns, right? N vapor phase composition, N liquid phase composition, then V, then L. So you have 2n plus 2 unknowns that you can solve for. So you can formulate this large set of 2n plus 2 equations in 2n plus 2 unknowns, and you can use the Newton method to solve it. So that's one way of approaching this. An alternative is to do some analytical work. So what we do is we take those 2n plus 2 equations, for example, and process the symbols appropriately and reduce that system of equations to one equation in the unknown psi, where psi is equal to V by F, the ratio of the vapor flow rate to the feed flow rate. That is the symbol psi. So you can reduce this problem as a problem where you have to find out psi. Once you find psi, then you can multiply psi by F to get V. Once you get V, you can get L as F minus V. So you've got V and L by now. Then you can make use of some of the relationships that are given there. For example, xi is given in terms of f, zi, ki, and psi. The relationships are given in the question related to that problem. So you can take a look at it. I will also point them out to you. And once you get xi, then you can get yi as ki times xi. So in the former approach, you take the 2n plus 2 equations and solve them using Newton method to get all of them simultaneously. But if you follow an analytical approach that I have described here, then you can first solve for psi, and then you can solve for V and L, and then you can solve for xi and then yi in a sequential order. So you can either adopt what is called the simultaneous approach of solving all the equations at the same time, or you can follow a sequential approach to finding out the unknowns. In some cases, the sequential approach may be possible, but the simultaneous approach will work all the time. And the simultaneous approach is often what is used in simulators like Aspen, HISES, etc. I just want to point out that the description is given in the question. Please look at tutorial 6 question. So the exact flow through of what I've just said, right? Writing mass balances, writing the mole fraction constraints, right? Because the mole fractions of the liquid stream and the vapor stream, the mole fractions of each of those streams should add up to 1. So those are the mole fraction constraints. The thermodynamic equilibrium is what I explained here, right? In general, Ki is a function of temperature and pressure, but in the simple case where we have isothermal flash process occurring at a constant pressure, then Ki's can be regarded as simply as constants, and the values are given in the question here. The feed fractions, the mole fractions are all given to be the same as 0.25. So these are the all the equations that you can write and you can solve to find the unknowns in the problem. But you can do this analytical work. So this is the expression I've been saying, how once you have found out VL, then you can find out Xi. And once you find out Xi, then you can use this relationship to find out Yi. So everything that I've said there should make sense to you. What we are showing here is the process on how we do the analytical work using the relationships that are given to kind of come up with this equation first. So the whole set of equations reduces to the simple summation involving the nth species, and then you denote the symbol psi, which is equal to V by F. And once psi is equal to V by F, we know 1 minus psi will be L by F. Please note that L plus V should equal F. And therefore, if psi is V by F, 1 minus psi will be L by F. Because if you add psi and 1 minus psi, you will get 1. So if you add the right hand sides V by F and L by F, you will get V plus L by F, which will equal to 1. In any case, you get this, right? You get this expression. This is what is mentioned in the PowerPoint slides as well. Now, this is the strategy that I was talking about, the solution strategy. First, given Ki values and Zi values, solve this equation to get psi. That's going to be a nonlinear problem, right? Nonlinear, a single nonlinear equation. This is a single nonlinear equation. You have multiple terms because you're using summation. So you'll have multiple terms, but it is a single nonlinear equation. So it's one equation and one unknown. You can solve it using F0 or Fsolve, or you can use the Newton method, or you can use the bisection method. You can do any of those approaches to get psi. So once you find out psi, then you can use these definitions to get V and L. Of course, you have to assume a value for F. You can assume that you're using a value of F equal to 100 or 1000, right? Your choice. I think I've chosen F is equal to 100. That's the basis for calculation. So we have assumed a value for the symbol F. All right. So once you get L and V, then you can get Xi. Where do I get Xi from? I go to this particular expression, right? I go to this expression that you see there. Xi is equal to F Zi divided by Kiv plus L. I've assumed F to be 100, Zi to be given in the problem 0.25 in this particular example. Ki values are given for each I. V and L I've just calculated. Therefore, I can use this expression to find out Xi. I goes from 1 to 4 here. Once I get Xi, then I can find Yi using Yi is equal to Ki times Xi. So that is the solution strategy, which I've also outlined. Let us see how we get it done in a tool like MATLAB. So this is the expression taken from the question, and I'm just rearranging the denominator of this function in a slightly different way. Ki times psi plus 1, and then you have a minus psi, right? Minus 1 times psi is minus psi. So I've just represented the denominator in a slightly different way without distorting anything. So in this particular question, I goes from 1 to 4. So that is what I've expanded here. So I've got rid of the summation by expanding the summation. So it's going to be 1 minus K1 times Z1 by K1 minus 1 times psi plus 1. That's for I is equal to 1. For I is equal to 2, you get the second term. For I is equal to 3, you get the third term. For I is equal to 4, you get the fourth term. So that should equal to 0 because that is what you see here. Now, what I do is I plug in the values for K1, K2, K3, K4 and Z1, Z2, Z3, Z4 given in the question. right? Ultimately, I'll do that. But interestingly here, Z1, Z2, Z3, and Z4 are all the same and equal to 0.25. Okay, so I'm just going to keep Z1, Z2, Z3, Z4 in the equation still, but I've substituted K1 is equal to 2, K2 is equal to 1.5, K3 is equal to 0.5, and K4 is equal to 0.2, right? So I've done that, and then I get this expression. Now, I said luckily Z1, Z2, Z3, Z4 are all the same here. So that's a common term from each of the terms in the equation. So I can get rid of that, right? Because you can assume that I'm assuming all of them to be the same symbol Z because the values are same in this particular question. And therefore, Z1 is equal to Z, Z2 is equal to Z, Z3 is equal to Z, and Z4 is equal to Z. And then I divide throughout by Z, and Z is not 0. So I can divide throughout by Z, and I can get this expression. I've just replaced the Greek symbol psi with the English symbol Q, right? So just to make sure that I can easily program it in MATLAB. So this is the equation I'm trying to solve. So as you can notice, this equation is a nonlinear equation in Q. And perhaps you can even guess the number of roots this will have. If you take the LCM and then do the processing of the numerator, you should get 3 roots for this problem. I suppose you can see that. All right. In any case, this is a nonlinear problem which you can further simplify and use the roots command to get the answer. So roots is one way of solving it because you're going to get a third order polynomial in Q ultimately, and you can solve for the roots of the polynomials using the roots command in MATLAB. So that's one choice. The second choice is purely trial and error. The other choice is bisection method, right? Interval halving method that we have seen many times in the past. We can also use something called the secant method, which we will take a look at. We can also use the Newton method, which we have just learned. All right, so all of these possibilities exist to solve this problem for the value of Q. So here, I'm just showing you at least 2 ways in this particular slide. So what I do is I first use the symbolic toolbox. I declare symbols to be K1, K2, K3, K4, Z1, Z2, Z3, Z4, and Q. And I say all of them are real values. And then I write out this expression for F, which is basically this summation that you see out there, right? So that is what is in F. So make sure you do it term by term and carefully, because if you program in the wrong function, you might be solving the problem correctly, but you may be solving the wrong problem. So make sure you put the brackets at the right places. You faithfully represent the given question in the form of this MATLAB command, right? So that's important. And once you write out the symbolic expression for F, what I'm going to do is I'm going to substitute for F in the expression F for K1, K2, K3, K4, Z1, Z2, Z3, Z4. I'm going to substitute those symbols by these numerical values. So K1 is equal to 2, K2 is equal to 1.5, K3 is 0.5, K4 is 0.2, Z1 is 0.25, Z2 is 0.25, Z3 is 0.25, Z4 is 0.25. So once I have this, now F will have only the symbol Q, right? Other symbols we have substituted some numerical values. So what I'm going to do is I'm going to solve for the values of Q using this VPA solve command. So VPA solve of F will give me the values of Q that satisfy F of Q is equal to 0. And then I also use this eval outside, right? Because when VPA solves for the values of Q that satisfies F of Q is equal to 0, it is going to leave the results as symbols. And we want the results in terms of numbers. And therefore, the eval command helps to convert symbols to numbers. So we get these 3 values for Q that we originally predicted, right? It is going to be a third order polynomial in Q, which will have 3 roots, and here are those 3 roots that are determined by VPA solve. Of course, some of these roots are physically meaningless while they are mathematically right. A negative value cannot be true for psi, right? Because psi is Q, that is nothing but V by F. So at the most, at the worst, V can be 0. Therefore, Q can be 0. Or at the best, V can be equal to F. It cannot exceed F. So in that case, Q or psi will take the value 1. So psi should be between 0 and 1. So this root is mathematically okay, but physically this is absurd. This is also physically absurd. So the physically meaningful solution is q is equal to 0.0949. The bisection method we have already looked at in the context of several problems. I'm not going to go through that again, but I've already provided the bisection implementation for this problem in this M file. So kindly take a look. So what happens is in 40 iterations, right, I get a value for the function which is of the order of 10 to the power of minus 13. So my convergence tolerance was 10 to the power of minus 12. So for a certain width of the interval, right, between 0.09492 and 0.09492, so there is no difference in the until the fifth decimal point, right? So we have bracketed the solution between these two values which seem identical for practical purposes, at which point, at the midpoint of which, you get the function value to be less than 10 to the power of minus 12 in magnitude. Therefore, we say convergence has been reached. So the answer is 0.09492, which matches with this, right? Which is obtained from VPA solve. So both the methods here give us the same value for psi, which is 0.09492. That means slightly less than 10% of the feed goes as vapor. 90% goes as liquid. So before going into Newton method, I just want to say how we might process the value of Q or psi that we have reached. So once psi is 0.09492 and we have assumed F is equal to 100, then V can be computed as 100 multiplied by psi, so that V will be 9.492 units. L will be F minus V, so L is 90.508 flow units. And then once we have L, V, and so on, I can calculate Xi for species I as F Zi divided by KIV plus L. This expression is given in the question. So what I can do is I can divide both the numerator and denominator by F, and then I will get this expression. Xi is equal to Zi divided by Ki psi plus 1 minus psi. I can group it up like this if you want to. Now, for every species I, we know Zi. For example, Z1 is 0.25. K1 is 2. And psi we found out to be 0.09492. Therefore, substituting those values, I can get x1 to be 0.2283. Kindly verify that. For x2, z2 is 0.25, k2 is 1.5, psi remains the same as 0.09492, so I can get x2 to be this. Likewise, x3 is this and x4 is this. So if you add up these things, barring round off issues, you will get 1. So the xi's should add up to 1. x1 plus x2 plus x3 plus x4 should make up the whole liquid stream. Therefore, the mole fraction should add up to 1, which it does. And then what I can do is I can exploit this expression. Yi is equal to Ki times Xi. Now all the Xi's are known and the Ki values are given. Therefore, I can find Yi. So that's how I can get all the unknowns in the problem. Now, when I implement the Newton approach for this, the Newton method for this, so that code is found in tut6p2newton.m. So kindly look at that code. So what happens is in about 5 iterations, I reach the answer. All right, so my initial guess for Q was 0.5, something in between. I thought 50% will flash as vapor and 50% will go as liquid. That was my initial guess, but Newton method worked with my initial guess, and luckily it was able to converge to the correct value which we got from other methods quickly in about 5 iterations. The bisection method took about 40 iterations, right, with our guesses. Of course, the number of iterations will also depend on your guess values. All right. So without being biased, I took this midpoint as my initial guess, and from there I got this answer of 0.0949 in 5 iterations. This is how the code for Newton method will look like. One way of writing the code. I'm not saying this is the only way of writing the code, but this is one way of writing the code. So basically what I do is I declare K1, K2, K3, K4, Z1, Z2, Z3, Z4, and Q as symbols, and I say they are going to be real. Then this is F1, the first term in the summation for species 1, for species 2, species 3, species 4. All right. Then the function, the total function is the summation of the four species terms related to the four species. So f is equal to f1 plus f2 plus f3 plus f4. And then what I do is, in that expression for f, I'm going to substitute for k1, k2, k3, k4, z1, z2, z3, z4. I substitute the given values. All right. So at this point in time, my f will be a function of q only, because all the other symbols have taken some numerical values. All right. And df, the derivative of the function, which is very important for the Newton method, because the Newton method is this, right? X new equals x old minus f at x old divided by the derivative at x old. So this is the Newton method, if you remember. So the point is, I need the derivative, right? I need the derivative here for calculating the correction vector. So this, what I'm circling here, is the correction vector delta x, including that negative sign. All right. So basically, I need the derivative. So I'm using the diff function in MATLAB and differentiate the function f with respect to q, differentiate it once. That means I'm looking at the first derivative. So df will now contain the derivative of f, and it will also be a function of q. All right. So we have computed both f and df. We have expressions for f and the derivative of f. Now we get into the Newton's iterations, right? The Newton method implementation as an iterative process. So here, as usual, I'm setting convergence flag is equal to 0. And Newton method will continuously keep improving until the convergence flag has turned to a non-zero value. Okay. I'm also keeping, as usual, a tab on the number of iterations by using an iteration counter. The iteration counter here, I've started at 1. And this is my initial guess, the starting guess required for the Newton method to start processing. So I've used an initial guess of 0.5. All right, so now we are setting the stage for the Newton method to start. So the Newton method will work inside this while loop, right? So inside this while loop is the Newton method. So this end is for this while. Okay, so this whole thing is the Newton method. The main equation is given here. It is like x new is equal to x old minus the value of the function divided by the value of the derivative of the function, right? So x old minus function evaluated at the current value of x divided by the derivative of the function evaluated at the current value of x. So that is going to be the new value. So I hope you understand what you're seeing there. So what you're doing here is, in the expression for f, for the symbol q, substitute the current value of q. And then what you do is you evaluate it in order to convert it into a number. You don't want for things to remain as symbols. You want numerical values. Therefore, what you do is use this eval. So this will compute for us f of x old. So this is the part that computes f of x old, the function value at x old. This part you do the same thing, but now in the expression for df, wherever you see q, the symbol, substitute the numerical value q old. All right. And even then, to make sure you get a numerical outcome, so you use the eval command, right? So this part computes f dash x old, the derivative at the current value of x, and this is the division that you see there. So x new is x old minus function at x old divided by function derivative at x old. So that's how you compute the new value for q. Now here is where you check for convergence. So if the gap, if the magnitude of the gap, so I use the ABS function, the absolute value of the gap. I do not mind whether q new is bigger or q old is bigger. I don't care about that. What I am looking at is the magnitude of the gap between my previous value of q and my currently computed value of q. If that difference in magnitude is less than or equal to 10 to the power of minus 12, this is my convergence tolerance. If it is smaller than that, I say, well, we have reached the solution. So I do not want the Newton method to iterate further. Therefore, I set conf flag is equal to 1. Because the moment conf flag is equal to 1, this loop will stop executing, because this loop executes only as long as conf flag is equal to 0. So I say convergence has been reached, and then I display the text here saying root has been found at q value at q is equal to whatever is the new value for q, right? I just convert it into a a string, and then I say it also happened in so many iterations. So whatever is the iter counter, I also convert that into a string, because this display, right, is basically it is going to display a string. So wherever I have numbers, numerical values, I will use num to str, number to string command, to convert the number into a string so that display can display it. Okay, this is only for display purposes. If the convergence is not reached, if the gap between Q new and Q old is greater than my convergence tolerance, then what I do is I do two important things. One is I increase the iteration counter. More importantly, to improve my unknown variable guess better, what I do is I'm going to assign Q old is equal to Q new. So whatever is the new value that was computed, I'm saying that's not good enough. So I'm going to assign Q old to Q new and then get back to this part where a new Q value will be calculated again. All right. So this is the idea behind this. This is a very, very critical thing. And this end is for this if, and this end, as I said earlier, is for this while. So this is the Newton method, a very simple implementation. Declare certain things as symbols if you have to, then declare the components of the function and then determine the function, right? So if you can type in the function directly, it's great, but I just thought I'll break the function into 4 terms, and each of those 4 terms I'll type out properly and then add all the 4 terms to get my function. So once you get the function, whatever symbols are known, you can substitute it, and then you can have the function ready in terms of the unknown variable. Once you have the function ready, you compute the derivative of the function using the diff command. And then what you do is you set the convergence flag to 0, you set the iteration counter to 1, you give an initial guess of 0.5 here. So these 3 things have to be prepared. Then you get into the loop. So in fact, right, this part is going to be the same for all problems. This implements the Newton method. All right, whether you call that variable as Q new, Q old, or X old, X new, it doesn't matter. This is the nice thing about it. So what will really change from problem to problem in any question involving one unknown in one nonlinear equation is going to be your function. Once you have the function correctly, maybe the numerical values of the parameters in the function can be different. So this is the part where you have to make the most changes. This part is going to be the same for all problems. All right, because you are going to calculate the derivative using the diff function of the function f. And you are always going to ask for the first derivative. So it's a matter of labeling whether you want to call the unknown variable as q or x or r, it's your choice. This is almost the same for every problem, these 2 lines. You can give different initial guess. This part is going to remain the same for most problems. So you have to make very minimal changes to solve new problems. Newton method, when you implement and you run it, you're going to have this answer in 5 iterations. This slide shows the results of the secant method. I've not described the secant method yet. So after I do that section where I describe the secant method, I'll come back to this example and show how the problem has been implemented here. So basically, to just give you a summary, by 6 iterations, right, I started with the initial guess of q is equal to 0 and q is equal to 1. Very much like the bisection method, I gave an initial guess for which the function value will be positive, and another initial guess for which the function value will be negative. So the 2 guesses are q is equal to 0 and q is equal to 1. Then what it does is using an approach that is called the secant method, which is different from the bisection method. So the secant method goes about calculating better guesses for the solution, and in 6 iterations it reaches the same answer, right? So that is the idea, and this is how the secant method is implemented. The file has already been shared with you, so you can execute it and see. I will describe the secant method later and revisit this piece of code so that you are comfortable with this piece of code as well. We will cross that bridge when we approach it. Thank you for your time.